Chapter 19 focuses on aldehydes and ketones. Now, we've already seen them before in the context of other types of compounds, both the reactions and preparation, but we're going to go through it in a more thorough and systematic approach. We're going to talk a little bit about structure and naming, then we're going to talk about preparation, and then finally reactions. In this video, we're going to focus on the general information about aldehydes and ketones. When it comes to naming aldehydes and ketones, we could use the common name or we can use an IUPAC name. So for the simplest aldehyde with only one carbon, the common name, this is formaldehyde. The IUPAC name, this is methanal. Meth means there is one carbon. The Al tells us that it is an aldehyde. With two carbons, this is acetaldehyde or ethanal. The next one, this is benzaldehyde. And the IUPAC name, benzene carbaldehyde, don't even worry about that. For small compounds, it's helpful to know the common names. And then once we get to larger compounds, and especially when we are looking at substituted compounds, then having the IUPAC approach is going to be much better. So here we have 1, 2, 3, 4 carbons. So this is butanal. Notice, we don't have to specify where the aldehyde is because by definition, it's going to be at carbon 1. Over here, we have 1, 2, 3, 4, 5. Because we're naming the compound as an aldehyde, the aldehyde gets the lowest number. We have a hydroxy group at position 3, and we have a methyl group at position 4, and then we write them alphabetically. So this would be 3 hydroxy 4-methyl pentanal. 3 hydroxy 4-methyl pentanal. There's a whole hierarchy of priorities. So, for example, an aldehyde has a higher priority than an alcohol or a ketone or an alkyl branch. So there are rules available, and you can use the book as a resource if you need it. For ketones, we have a common name. There is an IUPAC functional class name and an IUPAC substitutive name. The first compound, you should all know what this is. The common name is acetone. The next compound, this is acetophenone. For the functional class name, we are naming the alkyl groups and then specifying that it's a ketone in between them. So this is a methyl group and this is a methyl group. So this is dimethyl ketone. Here we would name the two groups, and so then we list them alphabetically. So this would be methyl phenyl ketone. And then the substitutive name, this is where we're going to name it as an alkanone. And so we have 1, 2, 3 carbons total. Our carbonyl is at carbon 2, so the substitutive name is 2-propanone. Okay, this is the most general type of naming, and so we can always use this one even when it gets to very large compounds. So this last compound on the right, we could call this an isopropyl and an ethyl, so we could call this ethyl isopropyl ketone. Or we could call it 1, 2, 3. It would be 2-methyl 3-pentanone. So we have 5 carbons total. There is a ketone at position 3 and a methyl branch at position 2. Just a couple more examples. So a ketone has priority over an alcohol, so we will name it as a 2-pentanone. And this is a hydroxy substituent, so this is 4-hydroxy 2-pentanone. And finally, this last one, we have an aldehyde and we have a ketone. So the aldehyde has priority over the ketone, so this is named as an oxo substituent. So we have 1, 2, 3, 4. This is butanal. And at position 3, we have an oxo. So this is 3-oxobutanal. So ketones have priority over alcohols, alkenes, alkyl branches, but aldehydes have priority over ketones. There are rules for all of these priorities, and I want you to be familiar with some of these priorities, and you can use the book as a reference when we get into more complex molecules. Let's think about the structure and bonding in aldehydes and ketones. So we know that both the carbon and the oxygen are sp2 hybridized. So that means that each one wants to have a bond angle of 120 degrees, and that is possible. And so the shape around the carbon is trigonal planar. The shape around the oxygen, if we're also counting the electrons, that will also be trigonal planar. Now, as we think about what this looks like together, so here we have an sp2 hybridized carbon. So here's an sp2 orbital, here is an sp2 orbital coming forward, and here's one going back. And then here is our oxygen with an sp2 orbital, an sp2 orbital coming forward, and an sp2 orbital going back. In addition, the carbon has a p orbital, and the oxygen has a p orbital. So here we have a sigma bond that's created by the overlap of a carbon sp2 overlapped with an oxygen sp2. And here we have a pi bond that's created by the overlap of a carbon p orbital with an oxygen p orbital. These are going to be overlapped with whatever the R groups are. And then these are the orbitals that will hold the lone pairs of electrons. Now, what can we guess in terms of the reactivity of carbonyl-containing compounds? While we write our carbonyl, we have to keep in mind that oxygen is more electronegative than carbon, so it will be pulling away electron density. So this means our oxygen will have a partial negative charge, and our carbon will have a partial positive charge. So in terms of reactivity, the carbon is an electrophile. So a nucleophile will want to react with it and share its electrons. The oxygen is basic. It can share electrons with something that's very acidic, for example. It's important to really think about the structure and bonding of aldehydes and ketones, in part so that we can understand their reactivity, so that a nucleophile will add to a ketone or an aldehyde. We will see some reactions later where the aldehyde and ketone will act as a base. So we need to really understand this reactivity. In addition, if we think about the fact that the oxygen has a partial minus and the carbon has a partial plus, what does that mean in terms of the stability of a ketone compared to an aldehyde? Well, this carbon has a partial plus charge, so it will be hoping for help from whatever groups are connected to it. So when we have a ketone, we have two alkyl groups that can both share some electron density with the carbon, and that is going to help to spread out this partial plus and stabilize the molecule overall. But in the case of an aldehyde, one alkyl group can help, but a hydrogen is not able to release much electron density. So a hydrogen is not going to help stabilize this partial plus, which means overall an aldehyde is going to be less stable than a ketone. As we're going to see later, this has important implications in terms of relative reactivity of aldehydes compared to ketones. Let's consider physical properties of aldehydes and ketones. So first of all, what type of intermolecular forces would we expect? Well, we know that we have a dipole, and so both aldehydes and ketones are held together with other molecules by dipole-dipole interactions. Remember, in alkane, we're talking about dispersion forces, and in alcohol, we have hydrogen bonding. Because we're comparing different types of intermolecular forces, we should keep our size the same. So these are as close as we can get in terms of the molecular weight. The experimentally determined boiling point, we're looking at 76 compared to 77 compared to 36 and 117. And so this shouldn't be surprising because we know that dispersion forces are the weakest, so it takes the least amount of energy to break them, which is why this has the lowest boiling point. The dipole-dipole interactions are stronger, but not as strong as the hydrogen bonding interactions, and so these have a medium boiling point. In terms of water solubility, both aldehydes and ketones are soluble, just like alcohols, and different from alkanes. So how is this possible? In terms of boiling point, it's not really that much like an alcohol, but in terms of water solubility, it's more similar. Well, when we're talking about an aldehyde compared to another aldehyde, then we are limited to dipole-dipole interactions. But when we're talking about an aldehyde or a ketone being able to interact with water, they are able, because of the oxygen, they are able to hydrogen bond with water. And so that will make them very water soluble. Next, let's focus on spectroscopy of aldehydes and ketones. So by IR, the most important thing that you're going to be looking for is the carbonyl, which is going to absorb around 1700 inverse centimeters. And so that should absolutely stand out to you. This is the only characteristic feature for a ketone. You'll see your sp2 or sp3 hybridized CHs depending on the structure of the compound, but this is all you're going to see regarding the ketone itself. For an aldehyde, you will have the carbonyl, but in addition, you will have the aldehyde CH. Now keep in mind, even though what we're talking about is an sp2 hybridized carbon connected to a hydrogen, an aldehyde is a special case, and so this absorbs, it's typically two peaks, around 2750 and 2850 inverse centimeters. Now 2850 is still in the range where we would see an sp3 hybridized CH, but 2750 is definitely too low to be an sp3 hybridized carbon hydrogen. So if you only see this, that doesn't really tell you anything. But if you see both of them along with the carbonyl, that tells you you have an aldehyde. For proton NMR, when we have a hydrogen connected to a carbon that is connected to a carbonyl, these tend to show up around 2 to 3 ppm. For aldehydes specifically, when we have a hydrogen connected to the carbonyl, these tend to show up around 9 to 10 ppm. Often, we can think of the carbonyl as a wall. So let's say we have some other neighbors over here. Well, often the carbonyl serves as a wall so that this hydrogen doesn't see these hydrogens. So often the aldehyde hydrogen will be a singlet because it is not split by the neighbors over here, and this set of hydrogens will not be split by the aldehyde hydrogen. They may still be split by something else over here. So often you do not see splitting, but not always. Sometimes you will see splitting in your aldehyde. Just remember that splitting is reciprocal. If this is not split by its neighbors, then it will not split its neighbors. Okay, so that it has to be consistent in that way. Next, if we think about C13 NMR, Our carbonyl, this is going to be very far left on the spectrum. These tend to absorb roughly around 200 ppm. And finally, with mass spec, because aldehydes or ketones will just have carbons, hydrogens, oxygens, there's nothing really special about isotopic ratios. So the M plus 1, M plus 2, there's nothing there that's going to really jump out at you. But what happens commonly is that from your ketone, you can have fragmentation here, which will lead to a C double bond O, which really doesn't look good, except that you can draw another resonance structure that looks like this. This might seem even worse because now we have a positive charge on the oxygen, but actually this one is better. This is a major contributor because even though oxygen has a formal charge of +1, everybody has an octet, and so that makes it pretty stable. So the stability of this carbonyl carbocation makes this fragmentation relatively common. And so you might look for a peak. Well, if you have a significant peak that's M minus something, that something might be this group that was lost. And so you can get some information from mass spec about that. There's a number of other common fragmentation peaks. Your book talks about the McLafferty rearrangement, and that's something that's really cool, really helpful. You're not responsible for that. So let's interpret some spectra. What should jump out at you right away is this signal just over 1700, and this is absolutely a carbonyl. We don't see any evidence of an OH, of a C single bond O, so it's not a carboxylic acid, it's not an ester. So look more closely, and here's our magic number of 3000. So all of our peaks are below 3000, but if you look more closely here, this is 2700. So these two peaks correspond to about 2750 and 2850. So this tells us that we have an aldehyde. And just in case there's any doubt, this tells us in NMR that we have an aldehyde. So looking at the proton NMR, this is our aldehyde proton. Here we have another signal at about 2.4, and this would be a hydrogen connected to a carbon that's connected to the carbonyl. This one would be further removed. This one would have to be at the end. Let's call this A, B, C, D, and the integration, this one integrates to 1 hydrogen, 2 hydrogens, 2 hydrogens, and 3 hydrogens. So what we're looking at then is this, butanal. So this would be signal A, this would be signal B, because it's next to the carbonyl, so it will be at the higher ppm. And notice the splitting. So it is split by 2 neighbors over here, but it's also split by this hydrogen. And we know that because this hydrogen is split by these neighbors. So on here, you can really just see it kind of as shoulders, but this is a very small triplet. And so this set of hydrogens is split by 1 hydrogen into a doublet, and then by 2 hydrogens into a triplet. So this is some kind of a doublet of triplets. But really what we can see is that it has several neighbors. This one integrates to 2, so this is another CH2 group. It's closer to 1 ppm, so it's not directly connected to anything, especially electron withdrawing. And it's hard to see how many peaks we have, but we can tell it has lots of neighbors, and that's what we see here. So this one must be C, and then finally this one would be D. It integrates to 3 hydrogens. It is a triplet that's leaning a lot, but still this is a triplet because it has 2 neighbors. When we look at C13 NMR, we have signal A, B, C, and D, and this is also consistent with butanal. So this is carbon A, and then carbon B. It's on the higher range, but still within the typical sp3 hybridized carbon. This one would be C, and this one would be D. And here's one more spectrum. Looking at the IR, we have our carbonyl peak. This should just be yelling at you. And then here we have our sp3 CH, and there's nothing else useful from the IR. So that's all the info that we get, but really that's all the info that we need. Looking at the proton NMR, so we have this kind of quartet. Is it a quartet? These don't really look very even. Then we have 2 hydrogens, 3, and 3. So we could try to play around with the ratios, but what looks more likely is that we have 2 signals that are similar to each other. Actually, let's look down here first. This would be a methyl group next to a CH2, and this would be a methyl group next to a CH2. I know it's methyl because it integrates to 3 hydrogens. I know it's next to a CH2 because each one is split into a triplet. But we have 2 different signals. So these are not 2 equivalent methyl groups. Therefore, we don't have symmetry in this molecule. So maybe what we have here are overlapping signals. So I'm going to call this signal A and B, C, D, E, and F. So for E and F, in both cases, we know those are next to 2 neighbors. So we have a CH3 next to a CH2. Here we have a CH3 next to a CH2. Here it looks like we have a couple of CH2 groups, possibly. Here we have a CH2 with a lot of neighbors. Here we have a CH2 with a lot of neighbors. Looking at the chemical shift, this one is about 2.4, or actually these 2 signals are at about 2.4. So this could be 2 signals on either side of the carbonyl, and these are pretty normal. So let's skip ahead and take a look at the C13 NMR. So this is our carbonyl, and I'm going to call that A, and then we have B, C, D, E, F, and G. So we know that we have at least an ethyl group and another ethyl group and some additional CH2s, and we have some things that are close to the carbonyl. So what if we had maybe 1, 2, 3 carbons? 1, 2, 3, because we have B, C, D, E, F, G, but this is symmetric. So maybe it looks like this. And then this is A, and then this could be maybe B, C, D, E. Oh, nope, because I have an extra carbon. So let's try again. What if we have this? Now, this could be A. One of these could be B and C, and then D and E and F and G. That is possible with the C13 NMR. Now, where do our proton NMR signals go? I'm not sure which one would be A, which one would be B. I actually don't think it matters. So let's say if this is A and this is B, that would work because we have 4 hydrogens total. And if this is C, it has a couple neighbors to the left, a couple neighbors to the right, so we would expect a multiplet. That works. And then this would be D, This has 2 neighbors to the left, 3 neighbors to the right, so this would be a multiplet. And then, not sure which is which, but we can call this one E and this one F. So E is a CH3 group, and it's a triplet because it has 2 neighbors. F is a CH3 group, and it's a triplet because it has 2 neighbors. So a little bit of trial and error was required, but we know that this is most consistent with the NMR data, and it also fits with the IR data. So I want you to get more practice working on interpreting spectra for aldehydes and ketones.
So that takes care of some general information about aldehydes and ketones.